Drag. Section 6. Drag is a force that opposes or retards the motion of an object as it moves through a fluid, such as air or water. So, we're slowing something down. You experience drag forces due to the air, which would be commonly called air resistance. That is a drag force. Whenever you run, bike, drive your car, swim, whatever, anytime you're moving through a fluid, you're experiencing drag forces. They are extremely important for microorganisms moving in water. The symbol for drag is D. It is opposite to the direction of the velocity, V, and it increases in magnitude as the object's speed increases. So, when we're dealing with drag, we have something called a Reynolds number. There are two basic causes of drag, first of all. If you throw a baseball, most of the drag occurs because the rapidly moving ball has to push away the air that's in front of it. So, therefore, this drag is due to inertial forces. So, forces that arise because the air's inertia makes it difficult to push through. So, you're pushing through the air and you're pushing away the air that's in front of you. That's one basic cause of drag. If you instead drop a sphere into a thick fluid like honey or molasses or something like that, it's very thick fluid, that's a viscous force that you're having to deal with, okay? The properties of the honey itself is causing the drag. The honey is grabbing the sphere and trying to hold it from dropping down. Gravity is trying to pull the sphere down or the ball down, but the honey or the molasses is trying to hold that sphere or that ball up. That viscous force is resisting the gravitational force. That is the second basic cause of drag. Okay, so which type of drag is more important? And the answer to that is it depends on the situation. So for drag due to inertial forces, the drag is proportional to this equation right here, or this expression right here. And each of these, they actually have a couple of, or a Greek letter here. This is a new Greek letter. This Greek letter represents density, and that Greek letter is the Greek letter rho, R-H-O. It's pronounced rho. It is always in science representing density. So the density of the fluid, and then times v squared, and that's velocity, and then times L, and L is just a measure of some size of the object, and the size probably is diameter. In this case, if you're talking about a ball, then it would be the diameter. For drag force due to viscous forces, so like the honey, the drag force would be proportional to this expression. And so in this case, we have another Greek letter here. This funny looking N shape is a Greek letter, and that is the Greek letter eta. E-T-A is pronounced eta. So eta is the viscosity of the fluid. And then L is, again, like the diameter or some measure of the size anyway. And then V is the velocity of the object. So the viscosity is higher in a thicker fluid. So something like water would have a lower viscosity. Something like honey would have a higher viscosity. Obviously, molasses, same thing, okay? So the higher the viscosity, the thicker the fluid. So the Reynolds number, remember at the top of the screen here, Reynolds number was the header. The Reynolds number is the ratio of the inertial force to the viscous force. So the inertial force is proportional to this expression, and the viscous force is proportional to this expression. And what we're going to do is we're going to calculate a Reynolds number by making a ratio of those two ideas, okay? And then we're going to talk about what does it mean when I have a high Reynolds number, what does it mean when I have a low Reynolds number. And that will answer your questions on, well, which one is more important. Okay. So the Reynolds number is abbreviated RE, and it is the ratio of the inertial force to the viscous force. So it is rho v squared L squared over eta LV. Now, there's some things that we can simplify here. We have an L squared over an L, so an L will divide out. And we have a V squared over V, so a V will divide out. So the Reynolds number actually simplifies to just this, rho VL over eta. Reynolds numbers are dimensionless. So it's like a coefficient. There's no dimension. Okay, when the Reynolds number is high, inertial drag is dominant. The numerator is bigger than the denominator, so the inertial drag is dominant. Inertial drag means the pushing force through the fluid is greater than the fluid trying to hold back whatever it is that's going through. So that's the dominant force. When the Reynolds number is low, then the viscous drag is more dominant. So the fluid is holding up that object more than the object is able to push the fluid out of the way. The density units, density is kilograms meters cubed, kilograms per meters cubed. Viscosity units are abbreviated Pascal seconds. PA stands for Pascal. Pascal is the unit of pressure. 1 Pascal is 1 Newton per meter squared. We'll deal with Pascals more later on. So right now, 1 Pascal is a Newton per meter squared, and then Pascal seconds would wind up being 1 Newton second per meter squared. Viscosity is very dependent on temperature. If you've ever heated up honey, honey is very, very tough when it is cold. But if you heat up honey, honey is very liquidy when it's warm. So warm honey would be less viscous and more fluid when it's warm. So the viscosity would drop as honey is warmer, and the viscosity would increase as honey is cooler. So therefore, the Reynolds number would be higher with warm honey and lower with cold honey. All right, so we have a problem here. We're going to consider a 75 millimeter baseball moving through 20 degrees Celsius air at a speed of 20 meters per second. We're going to calculate the ball's Reynolds number. Before we do that, we're going to look at this table. All right, so in the table, we have air at 20 degrees Celsius at sea level. We have rho, which is the density, remember, and we have eta, which is the viscosity given to us. And then remember, when we calculate the Reynolds number, the dimensions all drop out. So there you go with those numbers. Ethyl alcohol is here, olive oil here, water at 20 degrees, water at 40 degrees. Honey at 20 degrees, and then remember we warmed up honey, so it's at 40 degrees. Notice what happens. The density is the same for honey, and the eta, the viscosity, has dropped significantly. Water at 20 degrees, the density is the same, 1,000 and 1,000, but notice that the viscosity was 1 times 10 to the negative third, but then it was 7 times 10 to the negative fourth. So it actually did drop. The exponent was 10 to the negative third and then 10 to the negative fourth. So it got lower. Okay, so consider the 75 millimeter baseball moving through 20 degrees Celsius air at a speed of 20 meters per second. What is the ball's Reynolds number? So what do we got to do?
Well, let's write down the equation of
Okay, so the equation was up here. So Reynolds number, RE, equals rho V L over eta. Okay, now I can go back down and get my numbers. Ooh, okay. So, rho would be what?
1.2.
Okay, so we have 1.2
0.
kilograms. Okay, 1.20, yeah. Kilograms per meter cubed. Okay, now V.
That's 20 meters per second.
Okay, so 20 meters per second. Okay, L.
75.
Now, it says 75 millimeters, so what should we do?
Converted to meters.
Convert it to meters for sure. What is 75 millimeters?
0.075.
Is it 0.075
Is it 0.7?
or is it 0.75?
It's 0.75. No?
It's 0.075. Millimeters moves the decimal 3 places. So we go 0.075 meters. Okay, and then divided by what? Yeah, we need the eta for air, and that is 1.8 times 10 to the negative fifth. Now, that's Pascal seconds, but that's not going to do us any good for checking units. Pascal seconds is newtons seconds per meter squared, but newtons is kilograms meters per second squared, and then that's going to be times seconds per meter squared. So now everything's in kilograms, meters, and seconds. So this is just going to help us see that the units all divide out. Okay, so now let's do a unit analysis here so we can find our Reynolds number with no units. So let's just check. We have kilograms on top. We have kilograms on the bottom. The kilograms are gone. Now we have per meters cubed here, meters and meters as well on top. So the meters and the meters are gone, and the meters cubed is now just per meters on the bottom. All right, let's look at the bottom. We have a seconds and a per second squared on the bottom. So the seconds and the squared on the seconds are gone. On the top, we have a per seconds, and on the bottom, we have a per seconds. So per seconds divided by per seconds, those are gone. So all of the seconds are gone. Now, on the bottom, we have a meters and a divided by meters squared. So the meters and the squared on the meters are gone. Okay.
Those 2 meters divide out.
Now I have on the top a per meters, and on the bottom I have a per meters. So the per meters divided by per meters are gone. Do I have any units left?
No.
All of the units are gone. So that's good. I wanted a unitless thing, and I have a unitless thing. So now we can go ahead and do the math. Multiply everything out. What do we get? 100,000? Okay, so our Reynolds number is 100,000. Now, is that a high number or a low number?
Pretty high.
Well, it seems like a big number, but really have no idea relative to what, we don't
It's the
really
only one
know.
we've ever seen.
It's the only example we have. So this seems like a high number. A high number for a Reynolds number means what?
That the initial drag was. Yeah.
So it means the inertial drag is dominant, which means this ball, as it moves through the air, is pushing the air out of the way rather than the air is holding the ball back. And does that physically make sense?
Yes.
Yes, of course. Okay. So that makes sense. The answer makes sense. All right. So when the Reynolds number is over 1,000, it is considered high. All right. So I'm just telling you that. A high Reynolds number means the drag arises not from viscosity, but from inertial drag. This is true for most ordinary objects like balls, cars, planes, moving through air at ordinary speeds. Reynolds number is high for fish and for large objects moving through the water as well. So water is not considered a very dense thing for normal objects moving at normal speeds. For high Reynolds numbers, the drag force for motion at speed v is this equation here. So for high Reynolds numbers, the drag force is this equation. D equals 1/2 times this CD. This is the coefficient of drag. Times, what is that letter? That's rho. Times A. That is the cross-sectional area of the object. So that'll be meters squared. Times V. That is the velocity squared. Okay? And this will be opposite in the direction of motion. So, like I said, A is the cross-section area of the object in meters squared, and CD is the drag coefficient, and that depends on the object's shape. Streamlined aerodynamic objects have a lower coefficient of drag, of course. So I give you some common drag coefficients here. A commercial airliner has a drag coefficient of 0.024. They are very streamlined objects. They have to be, otherwise they won't fly. Also for fuel efficiency. A Toyota Prius has a drag coefficient of 0.24. Not nearly as streamlined as a commercial airliner. It does not need to fly, but it wants to be fuel efficient, so it is pretty streamlined. Pitched baseball, drag coefficient of 0.35. It should be pretty streamlined. It's a sphere after all. A racing cyclist tries to minimize their drag coefficient. If they can get their drag coefficient as low as possible, then they will be faster because they're not pushing as hard through the air. A running person has a drag coefficient of 1.2. They are basically a standing bar trying to push through air. If they can streamline themselves, then they will be faster. If they can't streamline themselves, then they won't be. They're pushing through air as a standing bar, okay? They just don't have a chance. So, biologists have estimated the drag coefficient of a swimming penguin by observing the rate at which a penguin's speed decreases in its glide phase. They actually sat there and studied swimming penguins. So the glide phase is when it's not actively swimming and is slowing down. So in one study, a gliding 4.8 kilogram, I don't know if it's Gentoo or Gentoo, penguin has an acceleration of negative 0.52 meters per second squared when its speed is 1.60 meters per second. If its frontal area, so this is measured, is 0.020 meters squared, what is the penguin's drag coefficient? This is a pretty straightforward problem, actually. What are we going to do?
Use the drag equation.
Use the drag equation, that's it?
I think so.
Almost.
We don't see the Reynolds.
We're going to do a sum of the forces in the x direction. Because we have a force in the x direction. What is the force? Drag. It would be in the negative direction because it's opposing the positive motion. So the sum of the forces equals negative d. And we have an imbalance of forces because we're slowing down. So that will equal mass times acceleration. Okay? So now, if I solve for d here, d equals negative mass times acceleration. They gave us the mass. It's 4.8 kilograms. So we have negative 4.8 kilograms times the acceleration, which they gave us was negative 0.52 meters per second squared. What do we get?
Positive.
It will be positive. Okay, so 2.49 would become 2.5. We only have two significant figures here. So 2.5 newtons. Keep that calculator answer of 2.49. All right, so now we know the drag has a force of 2.5 newtons. Now we can use the drag formula that we just had. So if I just bounce back here real quick, our drag formula, we had to calculate that force, okay? Now we can use that equation. So drag equals 1/2 times the coefficient of drag times rho times A times V squared. Okay, now what is it we're looking for?
The coefficient of drag.
Looking for the coefficient of drag. So I want to solve for C sub D. So how will I do that? So I'm going to multiply by 2 and then divide by
Everything else.
everything else. So I'm divided by rho, cross-section area, and V squared. And that's going to equal C sub D. Now, I know the drag force. I just calculated it. Do I know rho?
Yes. Rho is, well, I don't know, we don't know which answer it is.
Okay,
It doesn't matter, it's 1,000.
it doesn't matter. It's 1,000. That's right. Do I know the cross-section area?
So what importance is
Yes.
that?
Yes. And do I know the velocity?
Yes.
Yes, I know everything then. I can plug all this stuff in. So I have 2 times the 2.5, but I'm going to use my calculator's answer, 2.5 newtons, divided by the rho. What is the rho?
1,000.
1,000 what?
Kilograms
Kilograms
cubed.
per meter cubed. Okay, times the A. What is the A? 0.020, yes. 020 meters cubed or squared?
Squared.
Squared. And then the V squared, what is that?
1.6 meters a second squared.
1.60 meters per second. And then that is being squared. Okay.
And,
0.0975. Significant figures would take us to what?
3
We have 2, it looks like. So 0.0, oops, 0.098. Now, do the units come out the way we want them to? How many units, what should the units be here? We should have none. So I have just newtons on top, so I should wind up with newtons on the bottom as well. So I need kilograms meters per second squared. Over here, I get meters squared per second squared. So there's my per second squared. I have meters squared here. I have meters squared here. So I have meters to the 4th. On the bottom, on this first one, I have meters to the 3rd. So meters to the 4th divided by meters to the 3rd becomes meters. So I have kilograms times meters per second squared, which is newtons. Newtons divided by newtons divide out. So I'm good. I have a unitless answer. 0.098 is my answer, and I'm good.